Welcome to the learners for the video lecture on the topic specific heat capacity. Myself, Dr. C. Sridevi, Assistant Professor, PG and Research Department of Physics, Sri Sharada College for Women, Autonomous, Salem 16. What is heat capacity? Heat capacity is the heat required to change the temperature of the material. Suppose Q amount of heat is given to the material, the temperature rise in the material is del T. So heat capacity is given by Q by T, where Q is heat supply to the material, del T is the change in temperature. Next, unit of heat capacity. So the unit of heat capacity is amount of energy supplied to rise in temperature. Unit of energy is joule. The rise in temperature, unit of energy Q is equal to joules, and rise in temperature is given by Kelvin. So SI unit of heat capacity is joule per Kelvin. You see this figure here. We take a glass of water and another image is C. So here smaller mass, the heats up faster because we take a glass of water, the mass is too small. So when we keep this glass tumbler in the sun, it heats up faster. Suppose you see the sea water, it heats up very slowly because of larger mass. So heat capacity depends on the mass of the material. If mass is too small, it heats up faster. The mass is large, it heats up very slower. Then another one is the heat capacity depends on the type of material we are using. Here we take two different materials. One is gold, another one is aluminium. We take the same mass, 1 kilogram of gold and 1 kilogram of aluminium, but uh, we apply the same amount of energy or same amount of heat to this both the materials. The gold heats up very faster when compared to aluminium. So in this observation we see that gold heats up 7 times faster than aluminium. So amount of heat energy absorbed by the material or amount of heat developed in the material depends on the type of material. Here one more thing, example we have shown here. One is gold, another one is water. Here we take 1 kilogram of gold and as well as 1 kilogram of water. We are supplying same amount of heat energy, but gold heats very much faster when compared to water. Water takes 30 times longer, 30 times um, 30 times long time to heat when compared to gold. So it indicates the water stores 30 times more heat energy as compared to gold. Heat capacity. Heat capacity is given by Q by del T. Q is energy supplied to the material. Heat energy supplied to the material. Del T is the change in temperature. Next is specific heat. What is specific heat? Specific heat is the heat capacity per unit mass. So we are dividing the mass with the heat capacity. We get the specific heat capacity. Specific heat capacity equal to heat capacity by mass. The formula for heat capacity is Q by del T. So what is specific heat? Heat capacity by M. So the formula for specific heat capacity C equal to Q by del T into M, or Q by M into theta. Specific heat capacity is not same for all material. It is constant for a given material. It varies from it varies with respect to the material. The next, specific heat. How we define the specific heat? Specific heat is defined as quantity of heat required to raise the temperature of unit mass of the substance by 1 degree. How much heat is required to raise the temperature of 1 kilogram of the substance to 1 Kelvin. That heat is called as the specific heat. Specific heat is given by heat capacity by mass Q by m theta, unit of specific heat capacity. So what is the formula for specific heat capacity? Energy by temperature into mass. The unit of energy is joule, unit of temperature is Kelvin, unit of mass is kilogram. So SI unit of specific heat capacity is joule per kilogram per Kelvin. The specific heat of the substance is not constant and it is different for different materials. We are taking different types of materials. The specific heat also differs. Suppose we are using the pan. One is copper pan, another one is aluminium pan. The heat developed in these two pan differs because of the nature of the material. Copper heats very faster as compared to aluminium due to the specific heat. What is specific heat? Specific heat is nothing but how much of heat is easily absorbed by the material, easily accepted by the material is called the specific heat. Here I have shown the three different examples. One is copper, another one is aluminium, another one is water. See here we have taken equal mass, 1 kilogram of copper, 1 kilogram of aluminium, 1 kilogram of water, and also supply same amount of heat energy. But rise in temperature to 1 degree Celsius, time taken to raise the temperature differs from material to material. See here, water takes too much of time, long time to raise the temperature of 1 degree Celsius as compared to aluminium and copper. So water temperature rise in water is very slowly, then aluminium, then copper. In copper temperature is quicker as compared to water, and also heat energy stored in water is very much higher as compared to water because of specific heat. Specific heat of copper is 385 joule per kilogram Kelvin, aluminium 897 joule kilogram per Kelvin, water 4184 joule per kilogram per Kelvin. So different materials have varying specific heats which affects how they respond to heat input. Meaning the different material absorb different amount of heat because of their nature. So because of their specific heat capacity. In thermodynamics, specific heat capacity of a substance is the amount of heat that must be added to unit mass of the substance in order to cause increase the unit rise in temperature. Specific heat capacity means how much heat is absorbed by the material while increasing the temperature of 1 Kelvin is the specific heat capacity. Here for example 100 gram of copper and 100 gram of water are heated by using similar burners at the same time. The rise in temperature is not same for two cases. 100 gram of, we have taken the same mass, we are giving the same energy, but temperature rise is not same for this two substance. This is because of specific heat differs for this two material. The specific heat is not a constant. So rise in temperature depends on the quantity of heat given to the material, given to a body of mass and the nature of its material. Rise in temperature is not constant, which depends on mass and nature of its material. Let Q be the quantity of heat given to the body of mass and let rise in temperature be theta. Q equal to mc theta, where m is the mass of the material, c is the specific heat of the material, theta is the rise in temperature, Q is the heats given to the material. Specific heat of a substance is not constant. It depends on the nature of the substance. Factors affecting specific heat capacity. These are the three factors which affects the specific heat capacity. One is composition. So composition is the material chemical composition of the substance where the material is made of, suppose copper, aluminium, then water. Water contains hydrogen and oxygen. Copper sulfate means copper, sulfur, oxygen. So different composition of the material uh, affects the specific heat capacity. The next, state of matter. The physical state, that is solid, liquid, gas. Solid material possesses one specific heat value, liquid some other, and gas also specific heat value differs. It depends on the physical state of the matter. Another one is temperature. Specific heat capacity slightly varies with temperature for some materials. At low temperature, specific heat on the specific heat of the material shows one value. At high temperature, the specific heat varies. So these three factors affects the specific heat capacity of the material, that is composition, state of matter, temperature. Then here I have given the some examples of the specific heat capacity value of these some materials. Water 4182 joule per kilogram per degree Celsius. Aluminium 900 joule per kilogram per Kelvin. Copper 385, iron 450, glass 840. Importance of specific heat capacity. So where we are using this specific heat capacity? One is thermal energy storage. So materials with high specific heat can store large amount of thermal energy. I already told in this lecture, water has high specific heat capacity, that is 4182. So it can store large amount of energy. If specific heat is less, it can store only low thermal energy. Then next is temperature regulation. Substance with high specific heat capacity can help to regulate the temperature, like water in the human body. In human body, our temperature of the body is regulated by means by the water. Why water is used to regulate the temperature of the human body? Because water has high specific heat capacity, so it is used to regulate our body temperature. The next is calorimetry. Specific heat capacity is a critical parameter in calorimetry. It measures the heat transfer. In heat transfer is measured by using the specific heat capacity value. The next one is design considerations. So engineers design the different systems or different machines. So that design also that design have been carried out using different materials, that how they have chosen the materials based on their specific heat. Engineers consider specific heat capacity when deciding systems that involve heat transfer. Then measuring specific heat capacity. How we measure this specific heat capacity? First we take a sample. That is, we want to measure the specific heat of the some substance. First we measure the mass of the substance. Then we supply some amount of heat energy. Then we find out the temperature. So by using this method, we can measure the specific heat capacity of a given material. Then applications. Specific heat capacity is used in various places. I list out some few examples. One is automotive industry. Then second one is building design, cooking, meteorology. Automotive industry. In coolant systems rely on specific heat capacity to regulate the engine temperature. So whenever we are using the fuels in engines, it may heat up the engine. That heat is controlled by using coolant systems. The coolant system, what type of cooling system or coolant that based on the specific heat capacity of a material which is used to construct the engine. Then next is building design. Specific heat capacity is used in the is used to identify the materials for construction of buildings, because the some material absorbs more heat energy, some material absorbs less heat energy. So while in summer, if it absorbs more energy means we feel heat inside the building. So that type of thing have to be taken care while choosing the materials for building design. Next one is cooking. So cooking also we are using variety of materials in container used to develop the utensils. We are using copper bottom, aluminum beaker and all. So while in cooking purpose, we are using the materials which heats up faster. Which material which heats faster? The materials with low specific heat capacity. That type of materials have been chosen for developing the cooking vessels. The next one is meteorology. Specific heat capacity of air and water influence the weather patterns. So in meteorology also, specific heat capacity plays an important role. These are the fields we are apply the specific heat capacity: automotive industry, building design, cooking, and meteorology. Next, molar specific heat. So far we discussed about the specific heat of solids and liquids. The specific heat of solids and liquids does not change with temperature, or slightly does not change with pressure and volume, or slightly changes in pressure and volume. Solids and liquids specific heat change with the type of substance, but it does not change the type of process. So in solids and liquid, the change in pressure and volume is immaterial, because it is a um, um, rigid material. In gases, the specific heat value changes with respect to pressure and volume. If we compress the gas, the pressure increases. If we expand the gas, the volume increases. So if the volume and pressure play a major role in the specific heat capacity of a gas. So next is molar specific heat. Molar specific heat is the quantity of energy required to raise the temperature of 1 mole of the substance to 1 degree Celsius. Q equal to N into C del T. N is the number of moles of the substance, C is the specific heat, del T is the change in temperature. So here we are using two types of process. One is isobaric process. What is isobaric process? Isobaric process is one, the molar specific the process takes place when the pressure is maintained constant. That is, when quantity of heat required to raise the temperature of quantity of heat required to raise the 1 mole of the substance to 1 degree Celsius at constant pressure is called isobaric process. Next, isovolumetric process. Isovolumetric process, where we can we are using molar specific heat at constant volume. What is isovolumetric process? Isovolumetric process is one when specific heat is calculated at constant volume. What is specific heat at constant volume? Quantity of heat required to raise the temperature of 1 mole of the substance to 1 Kelvin at constant volume is called the specific heat at constant volume. So specific heat capacities of gas. Already I told the specific heat capacity may varies when we change the pressure and volume. If the gases are compressible, the specific heat may vary from 0 to infinity. If gas is compressed, and the temperature rises without supplying any heat energy to it. Suppose we compress the gas, the temperature of the gas is raised. So we are not supplying any heat energy. C equal to, already we know that Q equal to mc into theta, or C equal to Q by m into theta, or m into del T. We are not supplying any heat energy, so Q equal to 0. If Q is 0 means C equal to 0. So specific heat equal to 0, then Q equal to 0. Hence the specific heat. If we are allowed to expand freely, gas freely without any rise in temperature. So when we allow to expand the gas, so the temperature rise is 0, so del T equal to 0. We substitute del T equal to 0 in this equation, C equal to Q by 0, anything by 0, infinity. So specific heat equal to infinity. So the specific heat value varies from 0 to infinity while changing the pressure and volume. We are changing the pressure, the specific heat is 0. We are changing the volume, the specific heat is infinity. So the two specific heats are specific heat at constant pressure and specific heat at constant volume. Suppose we change the specific heat, pressure means the specific heat is very low. If we change the volume means specific heat is very high. These are the two limits, lower limit and upper limit of specific heat. So we can fix the pressure and find the specific heat, that is the specific heat at constant pressure. Then we maintain the volume constant and determine the specific heat, the specific, that is the specific heat at constant volume. The specific heat at constant pressure is defined as amount of heat required to raise the unit mass of the gas through 1 degree Celsius when pressure maintained constant. So Cp equal to del Q by del T at constant pressure. Specific heat constant volume. It is defined as amount of heat required to raise the temperature of unit mass of the gas through 1 degree Celsius when volume is kept constant. Cv equal to del Q by del T of V. So next, Cp is greater than Cv. Cp means specific heat at constant pressure is greater than specific heat at constant volume. The heat is supplied to a gas and allowed to expand at constant pressure. Then rise in temperature of a gas. Then second thing, it does work in expanding the gas against the external pressure. So heat supplied to the gas and allowed to expand at constant pressure means these two things happens. One is internal energy increases because of supplying heat energy. Then work done against the external pressure because we are maintaining the pressure constant. So we have to work done by increasing the for increasing the internal energy. Now dq equal to du plus dw. According to the first law of thermodynamics, dq equal to du plus dw. dq equal to heat supplied, du is the change in internal energy, dw equal to work done. So dq equal to du plus pdv. dw we can write it as p into dv, pressure into change in volume. When a gas is heated at constant volume, when no work is done, if we heat the gas at constant volume, we are maintaining the volume is kept constant, so no work done on the gas. So dw equal to 0. We put dw equal to 0 in this equation, dq equal to du. So hence whole heat is supplied is used to raise the temperature. Heat supplied is equal to increase in internal energy or rise in temperature. Thus more heat is required to increase the temperature of a gas through 1 degree Celsius at constant pressure than at constant volume. Here you see these two equations. At constant pressure, our equation is dq equal to du plus pdv. At constant volume, dq equal to du. So we compare this two equation. Heat supplied is equal to du plus pdv. So this much heat supplied is equal to change in internal energy plus work done. But here at constant volume case, dq equal to change in internal energy alone. We compare to this, PdV term is excess for constant pressure. So Cp is greater than Cv. That is, specific heat at constant pressure is greater than specific heat at constant volume. The work done term is excess in the specific heat at constant pressure as compared to constant volume. Then relation between Cp and Cv. Consider 1 gram of a gas at a pressure P, volume V and temperature T. Heat supplied to the gas to raise the temperature is dT. As the pressure remains constant, work done is equal to, what is the formula for work done? W equal to force per unit area or pressure into area, pressure into area into X. P into A is, P into A into X. A into X is the volume. Area into distance is volume. So P into dV. dV is the change in volume. From ideal gas equation, PV equal to RT. Differentiating this equation, P into dV plus V into dP plus R is a constant, R into dt. So we consider this process, the pressure of the gas remains constant. So pressure remains constant means change in pressure dP equal to 0. So this equation we may written as P dV equal to R dt. Work done is equal to PdV equal to W, which is equal to RdT. Work done in heat units is given by RdT by joule into calories. Next, heat supplied dq equal to mass into specific heat into change in temperature. Here mass is taken as 1 kilogram. Specific heat is Cp. We consider this process, the pressure is maintained constant. So specific heat at constant pressure, that is Cp, change in temperature is dT. According to the first law of thermodynamics, dq equal to du plus dw. dq is the heat supplied, du is the change in internal energy, dw equal to work done. For isovolumetric process means volume remains constant. So dq equal to du plus p dv, dv equal to 0. So dq equal to du. du equal to, du means increase in internal energy, which is equal to mass into specific heat into change in temperature. Because of internal energy rise, the temperature change occurs in the material. So we may write it as mass into specific heat at constant volume into change in temperature. So dq equal to du, which is equal to, we can take the mass as 1 kilograms, 1 into Cv into dt. We substitute this value in this equation. dq equal to 1 into Cp into dt. Substitute that value here. Then what is du? du equal to 1 into Cv into dt. Substitute that value here. Already we may find it out, Pdv equal to R dt by J. We substitute dw, instead of dw we can write R dt by J. So in this both the sides we have the term dt. You take dt and we take dt as common and strike it out. What are the remaining terms? Cp equal to Cv plus R by J. So Cp equal to Cv plus R by J. We bring this Cv left side. Cp minus Cv equal to R by J. R is the gas constant for 1 gram of gas. If Cp and Cv represent the gram molecular specific heats, then Cp minus Cv equal to R by J. What is R? R is the universal gas constant. The expression Cp minus Cv is R by J, which is the Mayo's relation. Mayo's relation relates the specific heat at constant pressure and constant volume. Cp is the specific heat at constant pressure, Cv is the specific heat at constant volume. That difference is equal to gas constant or R by J. Conclusion. The specific heat of solids and liquids depends on the type of material, but specific heat of gas depends on the type of process that we are using, that is isovolumetric process. In this process, volume maintain constant, and isobaric process. In this process, pressure of the material is maintained constant. Pressure of the gas is maintained constant. Cp is greater than Cv, that is specific heat at constant pressure is greater than specific heat at constant volume. From this value we can arrive the relation, that is Mayer's relation, which is Cp minus Cv equal to R. R is the gas constant, Cp is the specific heat at constant pressure, Cv is the specific heat at constant volume. That difference is equal to R. R is the Mayer's relation. Thank you.